All right, do you want to try sharing? So the YouTube is started, so you're...
Okay. As always, to make it full screen, maybe share first. Screen one.
Oh, pretty. Yeah, we see it. Okay, great. So we're very happy to have Sam Gralla. So since you may not know him, being if you are a fuzzball person, so he's very active in EHT and black hole imaging things, and will tell us about if we can actually see our fuzzballs or our other preferred models of non-black holes in current or future images. So please, Sam.
Okay, thanks very much. Yeah, so first of all, I'm not in EHT, but I've certainly been working in the area for some years now since the data came out, I guess, in 2019, which was a very exciting event. And I don't know if I'll tell you exactly whether you can see your fuzzballs or not, but I'll try to give you a sense of the basics of how these observations work, starting with the theory and talking a bit about the observations, and maybe also about some future ways that maybe we could actually get to, testing whether the metric is Kerr or seeing some other properties of the space-time, which then could, of course, tie into the microstructure stuff that people here are primarily interested in. So let me get going and start with just a sort of overview, get us going. Here's two different models of the black hole in the center of the galaxy M87. So this is the first one that EHT observed or published their results of observing some years ago. And these are EHT models that they use to understand their data, what they expect the source to look like. And I want to point out two features on this slide. The first feature is the sort of main ring, okay? And so notice the model on the left is quite different from the model on the right. The model on the left is narrower. It's also, in terms of its width, it's also smaller in terms of its overall diameter. These images are the same scale on the sky for that black hole. And so that is just looking at an accretion disk, matter accreting into a black hole, at a mostly face-on angle. It's brighter on one side than the other because of Doppler boosting from matter coming towards you on that side. But other than that, you're just looking at an image of a disk. There's really nothing fancy here. So that's the sort of model dependent part. It really depends on the assumptions you put in for your accretion flow. And these are two different Event Horizon Telescope models that show two different structures. And then there's this thing in the middle, which is in both of them and looks pretty much identical in both of them. And this is called the photon ring. This is the part of the image that's really universal. And I'm going to try to explain this in the talk. This ring will show up pretty much no matter what you put near the black hole. Now, it might be blocked by the matter. You might not see it. In this case, you can see it on top of the main emission because the emission is transparent to itself. But what you're seeing here is actually an image of the back of the disk. It's light that was emitted backwards away from you, was bent around the black hole, and came back to the observer. That's what you're seeing in this ring. And because that light has done all that bending, it's somehow more sensitive to the underlying geometry. And that really is probing the gravity, if you like, and not the sort of detailed assumptions you make about the plasma that's emitting and so on. And so probably for this crowd, the photon ring is really the super interesting thing. And maybe you're less interested in the details of the main emission. So in this talk, I'm going to focus mostly on trying to explain this photon ring phenomenon to all of you and put it in context maybe of what you're interested in. But for that, I'll need your help because you're not my community. I'd love to learn more. Unfortunately, I didn't come to the meeting this morning. It was in the middle of the night for me, so I'm not totally sure what you're into. So I do want lots of questions, which you can drop in the chat, or you can just unmute yourself and talk. It's a small enough audience. Okay, now just for those of you who have been following this, I do want to compare to a little bit of what is in the literature. Although my interest in this has become, my main focus, at the start, it was just sort of reading some claims in the papers that didn't seem right and then refuting them. And I think, there's a sort of half-life of these claims that I think our points are being accepted now and they're decaying. But, if you've still sort of seen these words about some black hole shadow or something, I just want to mention that that's most things that have been said about the black hole shadow in the data are not right. The dark area in the middle here is just the inner edge of the disk. There's nothing fancy determining it. It's just a hole in the disk. And this photon ring thing, which is super interesting, this narrow ring here, is subdominant. It has a minority of the flux. It's not what you're seeing in the image. It's there. It would be great to tease it out in the future, but you can't see it with the Event Horizon Telescope. So that's unfortunate, but I'm going to give you some ideas at the end of this talk for how we could see the photon ring with some space missions. In fact, I'm involved in a proposal to do that, and we'll get to that later. Okay, so that was my broad overview, and do feel free to jump in with questions. I'm going to make sure I actually do see the chat here on my screen. Okay.
Can you please elaborate on this false claim of shadows surrounding the photon ring? Because I was not aware of that, and I'm using this term.
You were not aware of the claim or aware of the fact that it's false?
I was not aware of your refutation of the claim. Sorry.
Okay, well, it's a little hard. That might be best left after. It's a little hard to try to state exactly what people have said and then why it's wrong. But the basics of it, and you can read about it in the paper with Holtz and Wald that I mentioned here from 2019. The basics of it is there was a belief that sort of no matter what matter you put near a black hole, as long as it's optically thin, meaning transparent to itself, that the dark area would be the size of the photon ring. So this photon ring here is a feature that really depends on the gravity. It's just I'm going to explain this more in the talk, the basic physics of it. I didn't invent it. It's, predates me by many years. But the dark area is totally distinct from that. So this little ring here is universal, but the size of the dark area on your image, maybe the next slide will make it a little more clear. Like, here's another EHT model. You can see the size of the dark area here is much, much smaller than the size of the ring. Yet for whatever reason, they claimed that even though it's not true in their models, they claimed that sort of the dark area was always the size of this big thing. It was a very strange historical chain of misunderstandings that I don't quite understand today. But people have looked at it more carefully. There's a paper led by Andrew Chale that just shows that indeed this little thing here is exactly the outline of the event horizon, not the shadow. And so, the point is when you see an image like this, the dark area is this is very blurry, but if you could resolve it more sharply, the dark area is just telling you the inner edge of your disk. It's not telling you something universal about the black hole space-time. If you want to know something universal about the black hole space-time, you have to resolve this narrow ring. Does that help?
Can I ask a question, or just to clarify? So okay, so I understand what you're saying, but would you say that the fact that there is a dark depression, which, let's say if you have infinite resolution, would be infinitely dark at the center, that's a telltale sign that there's a black hole, right?
Well, if you could see that it was infinitely dark, but of course there's some stuff in the way of you, right? So I think the depression is a telltale sign of the black hole. I'd have no objection if they called it the black hole, actually.
Right, okay.
It's not determined by the space-time. It's in any detail. It's determined by the fact that there's less stuff in front of you because it's a face-on disk.
Right. Okay. In that sense.
A hole in this. Now there are extra effects if there's matter infalling, and this contributed to the origin of the word shadow. The first model studied 20 years ago by Falke et al. Super interesting paper, not knocking it at all. They studied the case where matter is radially infalling in all directions. And there you do see a hole also from the fact that the matter in front of the hole is falling into it. And so it's Doppler dimmed because it's moving away from you. So that's also a sort of an effect that makes it dark there, even though there's stuff in the way. But yeah, the depression is excellent evidence for the lack of a surface. Emil, did you have a thought?
Yeah, so just a question about on the left image, could you remind me what's the angular resolution of that image and what are the prospects for improving it in the future?
Excellent question. I'll answer it in brief now, and I have slides on it later. So first of all, angular resolution is really not the right concept for this, because it's what an interferometer does is it has effectively resolution in the Fourier transform of the image. But there is a notion of effective angular resolution. I don't know if I can annotate, and it would be something like this. This is the roughly the effective resolution, the pixel size, but you still shouldn't sort of think of it that way. It can be misleading because it's really a measurement in the Fourier domain. And the prospects for improving it, there's two things you can do. You can add more telescopes, and there's something called, and EHT has already done this. And that doesn't really improve the resolution per se, because the resolution is kind of proportional to distances per telescopes, but between telescopes, or inversely proportional. But it will let you make a more reliable guess at the image. And then the other thing you can do is go to space. And now you can't put a swarm of telescopes in space, but what I'm going to talk about, an idea that I've been working on, is that with just one extra telescope far away, you could get some information about small scales, not a full image, but enough to tease out, in fact, the shape of this photon ring.
Okay, thanks.
Yeah, that answer will be more clear when I get to that part, which brings me to my poll. Now, I don't know my audience. I've got an hour nominally. I've used 15 minutes, maybe 10. So I've got 45 left. I can't do all three of these, but I want to know what you're most interested in. And then I'll decide how much time to spend on each one. So I just dropped a link here, some random website, the first non-ad result in make an online poll. And then drop that link in the chat. So you should all have a link in your chat. And if you could take a minute and tell me what you want to hear about most. Oh, someone popped up a poll.
Yeah, I
as
also
well.
put it, choice 1, choice 2, and choice 3.
All right, fine. Let's use Zoom. I take it all back. Thank you for the help. So let's use the Zoom polling feature. Never mind, use Zoom polling feature. It says 0 of 1 answered. Why would it be of 1? Has anyone answered the poll? It's called untitled poll, choice 1. Okay.
How did you
Yes,
answer?
I just clicked on that. I just made a choice. So
All right, so someone must see the responses then. So I'll talk for a few minutes while they fill in. What I mean by this is question A, understanding simulated images. Like if you want me to explain the physics of why that photon ring appears, I can do that. Understanding the actual EHT observations, like Emil asked about, I can get into the details of what they do and how you should, in my opinion, really understand it. And then part C is future work that could actually, how we could actually measure this photon ring, which would tell us about the space-time and maybe, microstate stuff indirectly.
unfortunately, co-hosts can't vote.
I don't need to vote. Oh, you can't vote. What's your vote?
I don't know. No, well,
Tell me your vote.
I vote for C as well.
yeah, I think the co-hosts are generally choice 3.
All right, +2 for
There was no option for all of the above.
No,
Yes,
just pick
that's true.
your favorite. We can stay late if you want to hear extra, but pick your favorite so I know what to focus.
Sam,
all right.
Sam, the deadlines aren't hard. We push them a little bit. So if you want to spend a few extra minutes,
Well, what I'll do is I'll finish early and then see if there's a million questions, and then we'll spend a few extra minutes. I don't want to.
At this point, choice C is overwhelming. I think it's 70%.
Okay, terrific. Choice C it is.
And 14% choice 1 and 2. So basically
Okay.
everybody wants to hear.
All right, so what we'll do is we'll go
Sure,
quickly
okay.
through A and B, and I will emphasize the parts of A and B that are in service of C. And do please ask questions to clarify as we go. Excellent. All right, thank you all for voting, and let's do it. So the first thing I have to do in service of C, telling you how we might measure the photon ring, as I just want to talk about what a camera is, okay? Because even I was confused about this when I started this project. And I'm nominally an astronomer, okay? All right, so cameras measure a function of angle on the sky, right? That's the first point. Your eye, wait, I want to annotate. Yeah, your eye is here, and you look in some direction, right? And whatever that direction sees, like this one, that angle on your sky sees the top of the teapot, and so on. All right. And so when you think about an image, you think about it of living in a plane, like here in the middle, in this image here, but it could live anywhere. It's just a sort of visual representation of a measurement of intensity as a function of angle on the sky. All right. And so the trick that we use in black hole imaging is we push the observer far away, and then the rays are basically parallel. Okay, and I emphasize this because it's not the way we usually think about it in like a book on optics. But this is more convenient to sort of turn it into a scattering problem. Okay, so if you put your eye very far away, off to the right here, then even though you're measuring a function of angle on the sky, the rays are coming to you basically parallel. The angle the error in replacing the black one with the blue one here is very small. Okay. And so you can actually imagine sending photons back to the teapot from, moving to the left, back to the teapot from your image, as if you're sending in a beam of photons in the scattering experiment. And you can see where those photons hit the teapot, and that defines your image. Okay. So that's the impact parameter image. And what does gravity do? Well, we want to think about bending of light now. So if we turn on gravity, again, we imagine sending our photons in from the right. We see where they hit the teapot, and then we assign to our image whatever intensity came off the teapot there to our image. So what happens if the light bends inward is the teapot looks a little bigger than it would without gravity, right? Because, for example, if we didn't have gravity, I wonder if I can make a straight line. I can't. If we didn't have gravity, we'd have a line like this. So without gravity, the lid would be here. So lid here without gravity. Okay. So you can see because of gravity, the teapot gets bigger. And this is the way everybody does ray tracing. It's just much easier to think about sending photons back from the observer to the source in this way, and impact parameter is proportional to distance on image. So that's going to help us get some intuition for what's going on. Now, of course, I wasn't the first person to think about scattering of photons in black holes. This goes all the way back to nominally, arguably Hilbert, but he didn't draw a picture. First picture was this guy von Lau in this GR-ish textbook in 1921. And it's just the same experiment. You're sending photons towards a black hole, okay? But what Hilbert and von Lau pointed out is that because black holes have these unstable photon orbits, if you aim very well, if you send in, this photon, what it'll do is kind of orbit for a bit, say, before escaping. And if you aim even better, it might orbit twice before escaping, and even better, it might orbit 3 times before escaping. And this is the distinguishing feature, at least among compact objects we know, of a black hole. A neutron star wouldn't have this feature. Its gravity isn't compact enough. Okay, so I sort of blazed through that, but now let's try to make sure we all get this slide, because this is going to be very important. Let's think about those photons that when we sent them in, these critical photons, they had just the right impact parameter to asymptotically approach this circular photon orbit near the black hole and orbit forever. So I'm going to call those photons critical, and they define a curve in your beam, right? If your beam is going into the page here on the right, there's a red circle where everything inside the red circle falls into the black hole, and everything outside the circle escapes. Okay. And the stuff very near the red circle, the photons near the red circle, will orbit before they either fall in or escape. And they'll orbit more and more times depending on how close they are to the red circle. And so in the inverse problem, where you're now imagining there's light sitting near the black hole emitting, this is the key point. Some of that light will have orbited before it reaches you, some of it, right? And where does that light that orbited end up on your image? Well, every photon that has orbited a little bit, half an orbit, one orbit or more has to end up on this critical curve. So you're always going to get extra light near this critical curve, extra images of the sources near there, or if it's a diffuse source, just extra light. Okay, so this is the hallmark of a black hole or some space-time with a similar phenomenon, that you'll see this ring. And Luminet here in 1979, I think, was the first person to actually make an image of something. And you can see here, there's the ring. The bottom of it is obscured, but the top of it is there. So the ring is the universal signature of the gravity in the space-time. The strong gravity bending light. It adds a ring. Okay, questions? People good with this?
Is
There's a difference whether the black hole is non-rotating or rotating, because then you have many rings, probably.
Well, you always actually have subrings in here. If your source is discrete, there's like one subring for each number of orbits. That happens for both Schwarzschild and Kerr rotating black holes. That's going to be important later. But in terms of this basic picture, it changes remarkably little for a Kerr black hole. Bardeen was the first person to work out the critical curve for a Kerr black hole. The math is much more complicated, but still closed form. At the end of the day, it's basically a circle. So very little effective spin. There's a little bit we can talk about, but not so important. Yes, Remy.
Yes. So this is the 3M, the 3M photon ring that I'm used to in Schwarzschild.
Well, I don't know what you're used to, but
It's
this
the
thing
top-
here is the photon orbit. This is R equals 3M
Yes, this is what I meant. But
photon orbit.
from what I remember, the angular resolution of the EHT figures is much coarser than 3M.
3M is actually not even the relevant scale for angular resolution. So let me add a few more things to this plot. So this impact parameter, this is about 5.2 M. It's the square root of 27. So that's the scale on your image. That's the actual apparent size of these photons coming from the photon orbit. So that's about 5.2 M. Now the EHT resolution is still lower than that, but higher than that, excuse me. So you can't really resolve 5.2 M. You can get sort of close. But the trouble with the ring is it's the width that matters. So looking down here at the width of the ring, that's what you would need to resolve. So the width is actually at most an M of that ring. And that width just has to do, actually there's a beautiful paper, it was Andy Strominger's idea, I think, but it's in a paper led by Michael Johnson about how the width of the ring is related to the Lyapunov exponent of the unstable photon orbits. I don't have slides on that in this talk. If we really stay late, I could dig them up from years ago when I was into that. But the resolution issue is really the width that matters.
So, but then I don't understand the figure, right? In the figure, you see a really well-defined photon ring.
Yeah.
The
Here, I have a slide on understanding the figure. So why don't you hold off your questions and let me try it. Here it is. So let me do this slide for 2 minutes and then ask your question again. So this is, okay, so here on the right is our modern version of von Lau's, plot of trajectories, where we pick only stuff that's coming in from the right. So our observer is at the right, okay? And now imagine that our observer is looking at a disk face on. So it says disk, and everywhere in this gray area, there's photons being emitted. Now the disk is also transparent to itself. That's almost certainly true at the actual source, so that's a good assumption. So photons can go through it. So let's think about what the observer sees. So near the middle of the image, over here, you guys can see my annotations, right? This red dot and so on. Okay,
Yes.
I sure hope so. Okay, great. So this photon sort of bends a little bit and falls straight in. So the image here is kind of dark. It's actually perfectly dark in this model because there's nothing in front of it. All right, and there's this photon. This photon goes like this, say. Okay, so this image, this part here, didn't leave myself much room to annotate. That part there is dim, but it's not, you can see a little bit. So you see inner disk, and it's also redshifted. So it's pretty dim. Redshift. Okay. And you can see as you go further out, and so that's this emission profile on the left here that gradually ramps up. So maybe I can put corresponding, that X might be here. I'm not going to be able to change colors easily on PowerPoint, so we're stuck with red. Okay, but then let's imagine what happens when we get to this photon. So this photon, you see the disk, but this photon bends enough. You also see the back of the disk. Okay, so imagine a photon emitted down at the back of the disk. Change to the mouse so you can see it. It goes around. Then here, some more photons get emitted in the same direction, right? These are the ones that just appear at the observer. And so at this point here, you see disk, front, and back. All right. And so it's only in this region of gold-colored rings where you can see the back of the disk. Because this region of gold-colored lines I've colored, those are the ones that bend at least 90 degrees. And so that is the shortest way to try to answer your question of why you see a well-defined ring. Because only a small portion of the light can actually orbit. It has to, the orbiting light has to appear only very near this critical curve. Did that help? You want to try again?
Yes, so my problem is with the scales. So on your figure, what are the scales and how do they correspond to the something like 10M resolution of EHT?
Oh, sorry. Well, these scales are 1M here, I think. 9, 8, 7, 6, 5, 4, 3, 2. Yeah, I think they're 1M. So I think this is 0, 1, 2, 3, 4.
So the disk size should be roughly 5M.
Yeah, this model we've picked that. So this full width half max here might be about 5M. Yeah, but the point is this photon ring is much smaller. It's
I
only
understand
1M.
that, but how does a telescope with a resolution?
It doesn't. EHT cannot see the photon ring. They said they did. They were wrong. It's just they can't. They were confused. They thought that the photon ring was dominating their image when it's in fact a small part of it and it's very narrow.
Thank you.
Sorry, I didn't realize that was the question. I could have answered that more easily. Other questions? Okay. So that was, okay, so this is me just showing that that toy model is realistic. So in brief, we sort of made this plot showing the narrow ring and discrete features. Nobody had made this plot before, at least not in the literature. And then we got an email a couple of weeks later showing us that actually this happens in the EHT models themselves. So our toy model actually really had all the features you need. And so that simple picture I showed you on the last slide is actually universal. Yes, someone was going to say something?
I was going to ask, so if we took your graph there and we applied a Gaussian blur to it with a radius of like 10M, that would be what would be an accurate depiction of what EHT is?
That would be a safe depiction. Because again, EHT observes in the Fourier domain.
Yeah.
But yes, that would be
Gaussians
safe.
in the Fourier domain or Gaussians in the real domain. So it's okay.
But their image reconstruction depends on choices they make in imaging algorithms, which are not just blurring the true image with a Gaussian. Let me, I promise I will get to that.
Okay.
That was my part B that maybe only you voted for. Okay. Right. So this is just sort of showing you what it would look like in a toy model. You see the main emission, you see the front of the disk, this n equals 1. And you also see another subring, which is you see the back of the disk. So let me do this. So this is front. And then this thing here is back. And then this tiny thing here is front again. And of course, there'd be infinitely many in principle. And so I mentioned this.
Can you put scales on this figure?
Yeah, same thing. So this, it's probably about an M. That's probably about an M, something like that. because the whole disk diameter needs to be effectively, I think it's roughly 10 m. Okay, and in microarc second, it's what you guys don't care about, but this is probably 10 microarc seconds. Okay. All right. Emil's question is coming soon. This slide, I probably don't need to sell this on you. So when I talk to astronomers or even physicists in general, I try to motivate, why we might want to measure this photon ring. And the answer is basically because it's the thing that's universal. And I think that's probably enough for this crowd. But as a second point, it really involves, you really will see differences with different metrics. So if you want to sort of get some data to help you, imagine if you had a measurement, you're working on your solution information paradox or whatever, and you had a measurement you had to reproduce. That could be super interesting. But anyway, that's pie in the sky. I don't think go here. Okay, so here's where we need to get to Emil's question, which is, if we were going to measure the photon ring, we need to think about what we're actually measuring. Okay, I get applause. Well done. You can use the emojis better than I can. So let's not think about this PR image. Okay, this image you see in paper 1 of EHT and the press conferences, this is like an average of their 10 favorite imaging reconstructions of each pipeline, then blurred, then averaged, maybe blurred again. It's a sort of vague sense of what's going on, but it's not at all close to what's actually measured. So here's what's actually measured. I'm not going to explain much because I need to get to part C of the talk. But what's actually measured, and it's a beautiful thing to go through, beautiful bit of math, is the Fourier transform of the sky. Okay, when you put two radio dishes, and each of them measures the electric field as a function of time, voltage in your piece of metal due to the oscillations induced by the incoming wave. You measure those in each dish. You represent as a complex electric field. You multiply and you time average a little bit. An amazing thing happens. It's like a miracle to me. Maybe for an optics person, it would seem natural, but to me, it's like a miracle. You just multiply the electric field time average, and what you get is the Fourier transform of what was on the sky. All right. So I here, the intensity is the image. That's what we talked about at the beginning with the camera. That's what's actually on the sky. And what you measure is a component of V. The Fourier, V is the visibility. It's just the Fourier transform. Okay. And so when you think about EHT's measurement, you should think about, number one, what is the Fourier transform of the sky? That they're in the direction they're looking at, there's an image. What is its Fourier transform? And what EHT measures is a bunch of pixels in the Fourier transform. Okay, and so the pixels are determined by the telescopes. I'm going fast, so I'm not going to explain it. But here are the Fourier space pixels on the right, bottom right here, for the EHT array as reported in the original M87 papers. So this is, they have at each dot, they have the Fourier transform of the image. Now, if I gave you a picture, I did this in a live stream on YouTube, actually, for fun. I can send you the link afterwards. We took a picture of a cat, and we took its Fourier transform, and we pretended we only knew its Fourier transform at these special points. And then we took the inverse Fourier transform, just filling in 0 everywhere else. You do not get a cat back. The only way you'll know there's a cat there is if you put a model for cats. You say, I'm sure it's a cat, and I want to know what kind of cat it is, okay? And I'm going to check whether the Fourier transform of my model for each kind of cat agrees with the Fourier transform I measure in these pixels. And that is what EHT is doing. Even if they call it image reconstruction, it's always a model, okay? They don't just take their Fourier transform, their measured visibilities, and compute the inverse Fourier transform. They can't do that. They don't know the inverse. They don't know the Fourier transform away from where they've measured it. So everything you see from EHT is some kind of model, some kind of assumption for what the sky looks like, which is then compared to the Fourier. They take its Fourier transform and they compare it to the data, and they see which does best. And it's not as hopeless as I make it sound, because it's not a cat on the sky, right? In this case, you have good reason to believe it's a ring, and you can train your imaging algorithms on shapes that are like rings, but also include other plausible image shapes. And they did this, and I think they did it well. And I think that means something coming from me, because I've been highly critical of their theoretical analysis. But I also looked at the data. My student, Will Lockhart, has a paper where we reanalyze the data. And I think what they did with it makes perfect sense. And we found the same results. So this is not a criticism. This is just a clarification. And if you look into the details of their paper, not the image they advertise, you see all kinds of images. Here's 5 different ones, 5 different things that are perfectly consistent with the data. It could be a really narrow ring, like on the left, could be a very thick ring, like on the right. The blob structure means nothing. The blobs show up everywhere. The robust features are that's a little brighter in the southwest. And I guess that's southeast, isn't it? Yeah, things are flipped left, right on the images. And the diameter is right. So basically they tried a gazillion different models, all of which made sense. And they always found a ring of approximately 40 microarc seconds. And so I'll let Emil ask again, but my strong suggestion is that when you think about the EHT results, don't picture that image. Picture some kind of thing like I've drawn here in orange, where you know it's a ring-like thing of about 40 microarc seconds, but you really don't know anything else. Okay, you don't know if it's narrow, broad, whether there's blobs, et cetera, et cetera. So Emil, does that help?
Yeah, it does help. And in particular, if I have my favorite, crackpot theory of what replaces a black hole, it sounds like this is not going to distinguish it.
No, not the EHT measurements. Absolutely not. The EHT measurements, I think I have a slide. Here's what I think the EHT measurements tell us. So sometimes people think I'm a downer. I actually think it's incredibly exciting. It's just you need to say a little less. So first of all, we can see the black hole. That's super cool, because if it were blocked by stuff, we couldn't do anything with it, right? Okay. Second of all, we get a nice mass range. That's nice. It really looks like a mildly inclined disk, which is what you expect from the jet angle inclination. That's an Astro thing, but that's pretty cool. But actually, for me, what's exciting is because the black hole is not obscured, that photon ring is in there. And if we want to test Emil's favorite crackpot theory, I'm sure it's not crackpot, then we need to be able to see that photon ring. And it's probably there. It's, we saw enough about the source to know it's transparent to itself with a high degree of certainty. So if we can build a better EHT, or an EHT that is tuned for a photon ring measurement, we might have a chance of constraining alternative theories. And so that idea.
So what's being, you said 5 different models on the previous slide. What's being varied in those models?
So this model here is a just simple model that allows, it's an analytic image shape model. So it just allows like a filled disk, but also narrow rings, thick rings, and things like that. And they just fit the 20 some odd parameters in that model to the data. And
is it just to make this short, is it different assumptions about what is emitting the light and where?
No, I haven't even done anything about what the source is like. I haven't tried to tie any of these images back to the properties of the source. This is just trying to guess what the sky looks like, irrespective of whether it's a black hole or a cat. So this is a model for what the sky looks like. And then you find the best fit parameters by comparing the Fourier transform of what the sky looks like to your data.
I see. So this is just different ranges of what the source, the actual sort of ground truth source could be, that is within error bars of the measured pixels.
Yeah, not even source. If you want to tie this back to the source, then you say,
I mean the image, the ground truth image.
Yes.
Yeah,
yes.
yeah. Okay, thanks.
Mm-hmm. Okay. All right. Okay. So right now we're heading into part C. And so, yeah, let's go through it. Okay, so how might we find a photon ring? I said some of this in words and we're running late. So, well, not late yet, but need to leave time. So the key point is, as has been emphasized, making an image is extremely hard. It was extremely hard to even do it as well as EHT did it, which is not going to test our gravity, right? But as a physicist, this is probably fairly natural to you. We should work with the direct observable, right? The thing you observe is the complex visibility. We take its inverse Fourier transform because humans are used to looking at intensities, not Fourier transforms, but of intensities. But you know, the thing you measure is the Fourier transform of the sky. We should work in the Fourier domain. And this paper here, Michael Johnson, and I'll also highlight Alex Lubchaska, who was a postdoc at Harvard at the time and starting a faculty position at Vanderbilt, and he's one of the real leaders in the theory of this. They just made this beautiful but very, very simple point that you'll see a signature of a ring if you go sufficiently high wave number in the Fourier domain, such that all the smooth stuff has already fallen off, right? Smooth stuff falls off exponentially, but not so high that you've also gotten rid of that narrow photon ring. There's a sweet spot of resolutions where you can see it. So this U, I haven't had time to really explain it. Think of this as telescope separation. There's a telescope separation sweet spot. Okay, where you actually would just see this narrow ring. Everything else would be resolved out, if you like. And that telescope separation sweet spot U, which I get it on this slide, telescope separation sweet spot, turns out to be at about the Earth-Moon distance. That's a vastly oversimplified statement about a bunch of papers we and others have written trying to pin this down, but that's the scale of this. So the idea is if we could add a telescope about as far away as the moon, we wouldn't put it next to the moon, actually. We just want it in orbit, but that's the typical distance. If we could do that, then what we would see is the amplitude of the Fourier transform, the thing you measure, would oscillate and decay. It would fall off with distance. And if we could measure a hop or two and get this distance between the peaks, so this is, you know, the telescope is actually moving because it's orbiting. We're changing the telescope separation, which changes the pixels on the Fourier plane. And if we could see this wiggle, it turns out, and this is a really nice thing that the Johnson et al. Paper worked out in a simple model, and I worked out in full generality following them, that turns out to tell you the diameter of the ring. So you wouldn't get a picture of a ring, but you would get an angle-dependent diameter of the photon ring. So we can go through some of this math later if people stay after the time, but for now I want to make an assertion and hopefully not lose too many people, that you make telescopes far apart, you measure this visibility, this Fourier transform of the sky, and depending on the line those telescopes make, where do I have a slide of this later? Oh, I don't. Yeah, here's a good cartoon of it. So you have one telescope on Earth, you have another telescope in space dish. Those define an angle phi in the plane of the source you're looking at. And what you can measure from those two pairs of telescope is this projected diameter here, this d phi, this angle-dependent projected diameter of the ring. Okay, so these are math people, these are the lines of support of the convex curve. I'm assuming it's convex for simplicity here on the plane. So that would be a term very familiar to, I don't know, is it 18th century mathematicians who worked all this stuff out for the first time? It's sometimes called the width of the shape. A shape can have angle-dependent widths. But this is the thing you can measure. And the nice thing about measuring this is you're not just showing, 50 representative images and saying we did our best, this is what it ought to look like. You're really in a situation which is more like a normal physics experiment where you're measuring a very precise thing. You can put error bars on it, as we've done in this forecast on the right, and you can compare it to the prediction. Okay, because this photon ring, as I said in the very beginning, really tracks properties of the space-time, the Kerr metric makes a prediction. It's highly circular, but not completely circular. And you can just, check whether the data agrees with the prediction. Question?
boringly practical question, but how big is, if you put a satellite out to the moon's orbit, how big is this dish going to be? And is it actually something we could reasonably expect to build?
Excellent question. There's two things that matter. Of course, the size matters for sensitivity. So the big size of the dish is going to be important, and also the detector quality. So with current detectors, you know, NASA has this TRL thing, technical readiness level. They don't let you fly things until you've demonstrated they work in simulated space environments or even in space. So we can only use sort of really well-established detectors, which aren't as sensitive to the cutting edge. If we have to use those, we need a huge aperture, like 10 meters. But check this out. There is actually an idea for this, which predated us. It's led out of Arizona, where I am, by Chris Walker. Dan Maroney, my collaborator on some of the theory papers, is the deputy PI. And we've added a space VLBI component of this. So this thing is a 20-meter aperture. It's proposed, but it's a legit proposal. It's a $1 billion, the call has been announced. Northrop and NASA Goddard are our partners. This is really happening. There'll be a proposal. It's basically a giant Mylar balloon in space. I'm sorry, I'm looking off screens because your picture is there. I can't help it. You know those Mylar party balloons that are like, just, they last forever? That's all it is. It's literally the same thing. It might even be made out of Mylar. It's just got a coating. So one side is transparent and you look through that. And then the inside of the other one is your mirror that focuses your light. And so if this is funded, it's mainly for far infrared science, because that's what the NASA call wanted, but at very little cost, we can add space field BI and do this. So if this is funded, we will definitely measure the n equals 1 photon ring. I don't know if that's good enough to test Emil Martinek's crackpot. Depends on how crackpot the metric. We all know Emil's not a crackpot, so I can make fun of him. He taught me quantum mechanics in grad school. I didn't do very well in that class, but he was clearly not a crackpot. But anyway, you know, and it's marginal for doing this second photon ring, which is what we assumed here. That's where you really can make an amazing plot. That will depend whether Saltus, that mission, can do it, will depend on, well, of course, assuming it's selected, will depend on mission design choices. It turns out they're not optimizing their far infrared mission to do my space VLBI black hole test, but you know, we can do our best, and we might get lucky with the source, so it's possible. But if we see this second photon ring, I really think you could make a plot like this. And you know, Emil's theory might have predicted. Well, no, it can't. It's really the shape. Oh, how do I undo? Oh, can't delete. Oh, I have an idea. Yes. Okay. And now I'm stuck on eraser. Okay, but you know, it could be that Emil's theory makes a different prediction for the shape of this photon ring. Maybe it's double peaked, right? Would probably still be symmetric. I drew a sloppy one, but you could imagine that the alternative theory had a different shape, and you could really just notice that it's excluded, right? So you could imagine distinguishing with this kind of measurement. Okay, this is actually not a bad slide to just sort of end on and take questions, because for question C, it really encapsulates everything I'm claiming you might be able to do, and we could see what more details needs to be explained. So maybe let's do that. Let's see if there are more questions.
Maybe can I jump on your shape and your two humped shape that you're proposing? So okay, so my question is really, do you have any idea how easy it is to get anything away from this this shape, right? Because this, I mean, so I'm asking because this is also something I'm trying to figure out, right? And it seems to me like it's actually kind of hard to go away from this kind of circlipse shape, as certainly for, you know, this 17-degree inclination or whatever, right?
Okay, we'll use the word circlipse. So you've read our paper, I guess.
Oh yeah,
that was a word. That was a word for the very, very precise shape that GR predicts. I think here it's really an ellipse. We can pretend it's an ellipse.
Sure.
Just for simplicity. And you're asking, in alternative theories, would they predict non-ellipses?
I guess what I'm asking, yeah. So what I'm asking is, how easy is it to get something that will not give you an ellipse, or even a more precise version, but still give you something that mimics other stuff well enough, right? Because it seems to me like you would need to go very far away from what you think a black hole would look like.
Yeah,
adds, yeah.
I think so. I mean,
yeah.
I mean the
but
one thing that's
the word eclipse has nothing to do with this curve. I mean, it's
ellipse. Sorry,
ellipse. It's not an ellipse. I mean, it's not squashed symmetrically with respect to the axis. It's squashed more on the side that it's coming towards us, and it's
yes, but that effect is highly suppressed at low inclination. So the belief is the spin of the black hole is only about 17 degrees inclined.
For low inclination or zero inclination is simply a circle.
Right. So this is closer to the zero inclination limit, and that's just M87. If we could, we think.
What I'm trying to say is that even for low inclination, it's not an ellipse. I mean, it's squashed on one side and it's a bump on the other side.
But you do have to, it's not magic. It's not like totally 100% independent of astrophysics. You do have to keep in mind, how this, at that level of precision, you're talking about like a part in 1,000, I think. That's the order of magnitude of how non-ellipse it is at this low inclination, something like that.
I don't think so. I mean, on the equatorial, for perpendicular, I mean, on the equatorial plane.
For perpendicular, yeah, but this is
a huge difference. It's a M difference.
But this is almost perfectly circular. Like 17 degrees is almost like you're looking at it head on, right? It's almost...
So this black hole, now you could do the measurement and find, and this is where you have to convince yourself you're actually testing GR, not modifying your model afterwards. But we could do the measurement and find that it is asymmetric, and the conclusion would be that it's a spinning black hole viewed edge on. But the belief, based on fairly strong evidence, is it's viewed mostly face on, and then the asymmetry is tiny. The astrophysics errors probably wash that out. You probably need to get up to a much, n equals 6 photon ring or something, but we won't do that.
But so do you have any sorry, just to press the correct, do you have any insights or intuition as to like, so I understand this is a great null test of GR, right? But like, do you have any intuition as to like how much this is going to tell us about models beyond GR?
I don't. I would like it if somebody worked on that. There is a postdoc coming to Arizona on a Fulbright next year, and who has some background in this, he might be interested. I was sort of, I don't know. I'm excited. It's my own work, so I'm super excited about this. I sort of expected there to be more follow-up studies. I thought everybody would be just busy computing the projected diameter of their favorite model, and we'd know the answer by now. It's not a hard, if you have models, it's not a hard calculation to make, right? It's pretty simple. It doesn't involve any astrophysics. You just compute the shape of this critical curve and then compute its projected diameter. So maybe it is always circular in everybody's favorite models, and that's why they haven't done it, but I don't know.
Can I ask a relatively model independent question? So we could presumably characterize the deviation of the geometry from Schwarzschild or Kerr or whatever by some set of multiple moments. And is it correct that the figure that you get in the end of the day that you're analyzing here on Earth is most sensitive to the low multiples of that deviation?
Not really, unfortunately, because multipoles are more of a far field concept, right? Whereas the whole point is this is probing, 3M or something, right? Where the multipole expansion doesn't really reproduce.
Look, but yes, absolutely. But the point is that if you have my favorite crackpot theory of black holes, right? The source is sitting well inside 3M, and the way it affects the geometry near 3M is through some set of multiple moments.
I don't know. I've never seen a set of multiple moments that predicts the geometry at 3M, maybe 10M, maybe certainly 100. But I don't know of any existing way to parameterize strong field deviations that is motivated like a multiple expansion. Multiple expansions are basically symmetry.
Okay, so yeah,
It's
well,
the
I just-
separability of the Laplace equation far
well,
away
it's,
that
I
gives
mean,
you
it's
multiple.
it's 3m versus m, so it's 1/3 to
Yeah, it could be.
higher,
It just
higher and higher powers.
there
So-
was some discussion of this because there were some claimed tests of gravity with EHT, which I don't believe. I think that's a non-starter. But if you accept that there's a test, you could ask, does it test multipoles or strong field? And there was some discussion in the literature. I think somebody actually showed that it really doesn't test multipoles, but I didn't really read the paper. I could send it to you if that's
Okay.
that's an important question for you.
Well, it's yeah. I mean, but it sounds like the measurements at the moment are so coarse that you could make a rather large deformation of the geometry at 3m and you wouldn't know the difference.
Oh, absolutely. Yeah, right. What you're looking at in EHT is a hole on a disk. Yeah,
Yeah,
you're not looking at any space-time stuff.
I mean, as much as you would like to use just EHT measurements, there are other measurements suggesting, right, for example, the evidence now for the first quasi-normal ring-down modes from the gravity waves suggests that the geometry near 3m is not that far from GR, right?
I'm not familiar, but the quasi-normal mode consistency test is an excellent prospect.
Right.
Yeah.
Now, my understanding of what you're saying is that this type of measurement constraints, I didn't understand what accuracy, the geometry or near 5m.
Yeah, 3 to 4m where the photon.
Well, the
orbits are.
3, right?
Yeah.
The 3, you don't see anything. So the photon ring is away from that. 4m, let's agree on 4m.
Okay, yeah, we don't. Yeah, so this is just another level of precision. I'm not knocking LIGO tests at all. LIGO is fantastic, and they've actually tested gravity now already with LIGO data, right? Strong gravity. Just the consistency of the first bright source with GR
Yes, so,
is fantastic. This is just a higher level of precision. So I do have these error bars drawn on here, and the scale here is 0.01 microarcsecond, right? So it really is tiny differences. I can't even draw them, right? So it's just it's not this. We have to do the mission. We have to get a little lucky to have a plot as beautiful as this. So it's not. It's unfair to compare to LIGO because it's better, but of course we haven't done it, and we need 10, 20 years of development to do it.
So
right?
I'm
But it is
trying
a high
to.
precision. Yeah.
Yes, what I'm trying to understand is in what sense this is better. What is it that you add? It's similar to the questions that Daniel and Emil asked. So I'm trying to convert your suggested measurement, hopefully it's done, to
It's really just precision. I mean, of course,
what?
You can think of the precision of this measurement as something like the size of the resolution over the size of the feature. Like how well. So discussing the precision of a null test is always a little dicey, right? You can easily say, if the points followed this red curve. No, let's do it this way. We could say, suppose we got the red curve, right? And we couldn't fit the data to it. So the data is still the black stuff, but the measurement is the red curve. Then what we would get is we would get a p-value, right? We would get the probability that the model describing the red curve is true given the data. And that would be, for this case, it would be like, I don't know, 0.01 or something. It would be excluded at a there'd be only a 1 in a million chance of whatever it is, 1 in, however you want to think about it. You can exclude the model at some statistical significance. And that's the way to think about the precision of the measurement if you exclude it, right? Now, if you don't exclude the model, if you just say it's consistent with GR, then you just have to sort of talk about how big these error bars, roughly how big the error bars is the precision of the measurement, right? Like if I had made this measurement, these were my error bars. It's still consistent with GR, right? Absolutely consistent with GR. Yay, I've tested GR, right? I mean, I think this is the only way to think about, the only way I found that satisfying to think about your question. If it's consistent, you have to say how precise it is by looking at the error bars. And so I think a natural way to say that would be, well, these error bars are roughly 0.1 microarc second. The scale you're probing, you know, is roughly 40 microarc seconds. So what percentage is that? 0.1 or 0.01%, something like that. And if you do that with LIGO measurements, you'll get a precision of maybe 5%. That's what they quoted for the original test. So, you know, it'd be a factor of 100 or 1,000 more precise. And the reason I think that is good is just that, you know, when theories fail, they don't always fail spectacularly, right? Often it's highly precise measurements that reveal discrepancies. And so if you're a physicist and you think it's interesting to probe gravity at the fundamental level, you really want to go for precision measurements.
So maybe Sam, can I direct your attention to the question in the chat? Because I saw that there's a question in the chat about the shadow.
All right, let me read it. I would like to get back to something you said all the way at the start. You said the black region in the center is not the shadow. Can the black hole shadow, as in the theoretical shadow, based on illumination from all around, be observed or measured? Or is there no hope to distinguish this from the hole in the disk? So basically, I think the question is, I have a slide somewhere on the theoretical shadow. I think afterwards. Okay. So if you were, the shadow references, the question references this contrived example, which is where the illumination is not a source near the black hole, but it's from all directions. The whole celestial sphere is lit up. Oh, but you're not asking about this, because this you would see brightness everywhere. I think, let me change your question. I think you're asking about this shadow. So the first paper that coined the term shadow considered radial infall. The matter is infalling, and the hole that you see is caused by redshifting. It's caused by the fact that all the light that would have arrived to you inside this critical curve would have been emitted opposite to the flow, and therefore is dimmed. So this is the sort of true shadow where you can see, those of you who know the flattened shape, you can see that this really even has the flattened shape. This is what started everybody talking about shadows. In this very specific model, where the matter is spherically symmetric and radially infalling, the dark area is exactly this critical curve. And so what I think your question is could we tell whether it's the original model, which actually has a shadow, versus the generally agreed upon belief now that the source is actually more like a disk, not a blob of infalling matter. So I'm going to say your question really is, can you tell a disk from a blob? And the answer is not yet, but I do think eventually, because the disk and the blob will make different predictions for other aspects of the observational appearance, say variability or, you know, fluctuation scale, spatially, like things we will measure as there are more and more observations, right? We've just had the first observation of a black hole, or now the second with Sagittarius star, but there's only one observation published with M87. There's going to be way more, but that's unfortunately very much an astrophysics question. I mean, I think it's interesting, but for this crowd, maybe not. So you could try to distinguish astrophysically and then argue that what you're seeing is the critical curve versus the event horizon or something, but I'm still not sure what you would learn about gravity from that exercise.
So I just noticed that it's that we're past time, but we should in any case thank you for a very illuminating and educative talk for us. So thank you very much.
Great.
Thanks.
If you're still up to it, we'll have some more questions if there are.
Yeah, I'll stick around. Sure. It's early morning for me. You guys are the tired ones. I got all day.
Should I keep the YouTube running or should I stop it?
Yeah, just keep it running for a bit. I think, yes. If I mean.
Yeah, I'll be nicer if I know I'm on YouTube.
Oh, okay. Oh, maybe that's the question. What would you say if you weren't on YouTube?
I can't say that now.
So maybe can I ask another question about the shape?
Yeah.
So you always showed, or you showed the 0 to 180 degrees, right? Because the rest of it will be symmetric and will give you the same thing. But would you, so what if we measure the whole thing and we see that there's some kind of statistical difference between, let's say, the 0 to pi and pi to 2 pi? That would be a nice smoking gun of not GR, right? Because that means you're breaking
Oh, that
kinds of
sounds like
symmetries that you're, right?
no. No, that means you did your measurement wrong.
What is
The-
that?
Okay, so the GR symmetry has to do with the 0 to 90 and 90 to 180. That symmetry. The 0 to 180 being the same as 180 to 360 is just the fact that if my angle were this one.
Oh, sorry. I 0 to 90, 90 to 100. Yes. Okay. Yes. Okay. Yes. So sorry, let me rephrase my question.
But you could ask it for 90 degrees. Yeah.
Yes. Let me rephrase my question. Because you might not be able to see is this a statistically better question to ask? Like trying to tease out symmetries like this and see, like, because your ellipse might be easy to fit an ellipse, or relatively easy to fit an ellipse within whatever accuracy you can measure these things. But is it easier somehow to tease out breaking of these symmetries, or do you have an idea how that?
Yeah,
would
I
work?
mean, I have a feeling there's some subtlety I'm not remembering, because what you point out sounds so interesting that we probably considered it, but maybe we don't. But yeah, you could certainly try to just test for symmetry, and that might be more robust and sort of convert multiple measurements into one, which would be conceptually easier to understand than fitting a curve. Yeah, I think the reflection symmetry about 90 is I guess
Also,
would be
but-
less discriminating, because
Right.
most non-GR theories would probably also have it. That has to do, I think the origin of that is the reflection symmetry of Kerr across the equatorial plane. It's been a while since I've thought about this.
Yeah, well, so your shadow is always going to be equatorially symmetric, even for a whole bunch of black holes that are not equatorially symmetric. So yes, that's surprising, but yes. Even if your image, right, forgetting about astrophysical asymmetries, even if your image is not equatorially symmetric because the metric is not equatorially symmetric, your shadow is often still equatorially symmetric, as long as your metric is integrable for geodesics or for null geodesics. Yeah. So you need to break both equatorial symmetry and integrability of geodesics.
Well, integrability, there's no, I mean, that's something we humans assume for convenience, right?
Exactly.
I can't believe that's
exactly.
okay.
Exactly. So yes, so
But
it is possible to
symmetry,
do it. Well, I
okay,
don't know.
good.
Why equatorial symmetry?
Well, at least it's a symmetry.
Right. So that's why we want to test if it's really there.
Yeah, I agree. I'm just
Yeah,
saying equatorial symmetry sounds, based on my bias and my training or whatever, it sounds more interesting to test than integrability.
Well, right, but what I'm saying is you need to break both to be able to test it.
Understood.
Yeah.
Interesting.
Okay. Anybody else have any more questions? Otherwise, we can sort of wrap up. Maybe I have some more follow-ups, but
Yes,
yeah, go ahead.
I still am trying to understand let's ignore for the moment the moon, because it's too far, and just concentrate on what you can do on Earth. So EHT projected a few years further. My impression is that it can basically say that if you have in mind some idea of modifying in a significant way the geometry inside, let's say 5-6M, then the HT measurement would not be consistent with that.
No, I completely disagree, and I'm on the record. I think it's bonkers, totally bonkers that claim has been made. I wrote it didn't occur to me anyone would ever make it because they didn't make it in the first set of papers, right? I mean, EHT did not claim to have tested GR in the M87 paper. Then a few years later, another paper came out. And so then I wrote a little single author refutation just pointing out that, you know, the uncertainties in the astrophysics are so much greater than, you know, our prior belief in the correctness of GR is so much higher than our prior belief in the correctness of whatever computer models EHT used. They're just the latest things you can code up. Everybody, they're fine, but they're missing all sorts of features. And, you know, astrophysics is hard. It's nonlinear plasma dynamics, you know, so I don't agree with any of
Very good. So great. So what is it that I can actually learn from EHT measurement, let's say projected a few years ahead?
I think from Earth, it's still really challenging to beat the astrophysics. I haven't heard and can't conceive of an idea right now that would let you decide that the radius of the observed emission ring or some other property you could observe from Earth is dependent on the black hole spacetime. And it's just so dependent on astrophysics. So from my guess personally is we will need to measure the photon ring to start testing gravity, because that's the universal feature of GR, the signature. There would have to be some evidence that buried within the larger emission ring is a narrower ring, and you'd have to know something about that narrow ring. So I don't know if EHT can do that from Earth. Maybe, but actually we've tried. My student who's actually looking at the data, our second paper, which will be coming out, just as an exercise, we tried to fit a model to the data that had the photon ring to see if we could get a better fit. It didn't work at all because the data is not good enough, but maybe eventually it will be. I just don't know. I'm sorry, I can't give a better.
No, it's fine. It's actually, this was my impression, but I didn't really look into details. And it's reassuring to hear you say that, well, if I now translate what you said, basically for purposes of space-time physics, it will be hard to measure anything.
Correct. Yeah. And you can look up my single author paper on this. It's highly non-technical, but it'll give you a sense of it.
Yeah, but since you already answered that question.
Oh, okay. If you can just believe me. Yeah, that's even better.
May I ask a question? It's more a curiosity than a question about the black hole in Sagittarius. The image looks very different from M87. Is there any interpretation of the new image?
It's just even harder than M87, right? I mean, this is what you should think of when you think of M87, right? Hundreds of different images they've made, which all look kind of different, but basically share a feature of a 40 microarc second ring. Sagittarius A star, they did the same thing. It's just even harder because the source is variable. So they actually did this. I haven't looked, I trust them because I did look at their analysis for M87 and it made sense, but they did this kind of insane thing with Sagittarius A star where they added a noise model for variability so that they could somehow use all the data, even though the source has changed significantly over. And they came up with, again, it looks mostly like a ring, and this time it's 50 microarc seconds. But I mean, I think you should think of what we've learned about M87 and Sag A star as this orange picture, except for Sagittarius A star, it's 50 microarc seconds, and we don't know that it's brightest on one side. We just know that it's about 50 microarc seconds. The picture they show, I mean, it's just the one they show to put in newspapers and, you know, paper one. It's not, there's no science in the picture.
Okay, thanks.
Anybody else have questions, or should we?
I just have a comment about your comment saying that we should focus on what is measured rather than all kind of invented quantities that are related to that. And we had the same issue. We were looking at the supernova distance measurements, and they were saying that they're measuring the cosmological constant and so on. And it turned out that they are measuring something completely different. And if you actually want to understand what is it that they measure and what are the errors, you should focus on the quantity that they actually measure. And for some reason, they tend to hide that quantity.
Interesting. I hadn't heard of that in cosmology.
Yeah, it's very common. So it was fun to hear you suggest that we look at the quantity that is actually measured.
Is there a raised hand as well now? Stem, do you want to?
Yes, can you hear me?
Yeah.
Hello? Yes. Hello, thanks. In fact, just to go on the record, I was the one that voted for B.
Did you get what you wanted?
Oh, thanks. I learned a lot.
Great.
I just wonder, but this is something that I'm still a bit confused about. What's the reason that there's this? I mean, you have this photon ring, and as you in your slide that you have right now on the screen, you say it's brightest somewhere to the south, brighter to the south. Question: why?
Oh no, that can be explained. That's one of the really nice things about the M87 results. The idea is, we believe, based on modeling of jets, like theories for how jets form. M87 has this spectacular jet of particles, right? Pencil thin beams shooting out bigger than the galaxy, coming from the black hole. Crazy thing. And the belief is that you'd have matter orbiting perpendicular to that jet, and then falling into the black hole, and that helps power it. And if you just assume matter is orbiting perpendicular to that jet, without any modeling, just the projection, the fact that you would then be looking at it at a certain angle will mean that matter from one side is coming towards you and matter from one side is going away from you.
Oh, I see.
And the brightness asymmetry and so that'll make it brighter when it's coming towards you, right? And actually I put somewhere over here because it's not very well constrained, but actually the expected brightness asymmetry is in that region. So it really does seem to confirm what, people have been saying about jet launching for many years. So it's really quite nice.
So could one reverse the argument and say that if the brightness were uniform instead of being somewhat not uniform, that could be, what could that be? What could that be an indication of? Assuming that it's a signal and not just some.
Well, it could be spheric. It could be that you're looking straight at the disk. That would be kind of fine-tuned.
That would be fine-tuned.
It could be that it's actually not a disk. It's just matter falling in kind of spherically from all directions, which is actually what everybody believed 20 years ago. I mean, I'm not an astrophysicist, honestly. I may seem like it in this crowd, but I just sort of read the paper. And 20 years ago, people said it must be radially infalling, and that's where this whole shadow idea was born. And then 20 years later, everyone says it should be a disk. I don't know. In 20 years, maybe it'll be something different. I really don't know. But if it were spherically infalling, you wouldn't see these redshift Doppler shift effects. You'd see just the gravitational redshift.
Okay, thanks.
So to follow up on that, I mean, are the slight color? No, I look at Sagittarius A star pictures, and they look like they got two or three bright dots. There's some brightening.
Yeah,
is that not something I should take seriously, or is that something?
They're totally dependent artifacts of imaging. They just really wanted a picture, so they showed you a picture. But you should think of what I have on the screen.
Okay, so the issue with Sagittarius A stars, it's presumably edge on relative to us, whereas it's
actually probably not, because if it were an edge on disk, you would see huge brightness asymmetries, and they don't see that.
That was the question I was asking.
Yeah, so it could be this spherical infall scenario, I guess. I don't know why it's disfavored. There's probably a good reason. I mean, or it could be that it's roughly face on. I think the line in the EHT papers is it's probably face on. I mean, the library of simulated models they used to fit it assumes it does.
I'm being very naive, but the jets in our galaxy go out the top of the bulge and down the bottom of the bulge.
Well, there's no visible jet, so there may not even be a jet.
I thought there were weak jets that we see from these very diffuse ones that we see.
Well, okay, the galaxy certainly has a symmetry, right? It's a disk. It's a spiral galaxy.
I know, but we're in the disk, right? And then
there's no observed jet that can be tied to the black hole. right?
Ah, okay.
So there may be features, but not like these AGN where you see this ridiculous stream of.
No, absolutely. But I
Right.
thought there were sort of wimpy, diffuse jets that people
Maybe.
have seen. Chandra picked. Wait a minute. It's the Chandra and Fermi. They picked up some kind of jet out of the.
Oh,
top
the
of that.
bubbles.
Yeah, the bubbles, but I
Yeah.
think there's something feeding the damn bubble, right? So therefore,
Yeah, but it's
surely,
probably not. I mean, it's pretty crazy that we even tie the jets in other galaxies to black holes. But the black hole is like a speck compared to the whole galaxy, and even compared to the jet after it's opened up. So I think the natural assumption is any feature you see is not due to the black hole at the center. You have to be dragged kicking and screaming to attribute to the black hole at the center. And the history of jets is that's what happened. People just couldn't understand a power source for these jets, and they had to conclude there was a compact object.
right?
So I don't think there's much. The only reason to believe the Sagittarius A star might be edge on is just that the galaxy itself has that alignment. But the dynamical mechanisms to align things with each other are myriad and poorly understood. I mean, in astronomy, even why does the black hole settle to the center of the galaxy is not well understood.
Sure.
So, I think you can't, you might be mildly surprised it wasn't edge on, but you wouldn't go, tell Stockholm, to give you a Nobel Prize.
Okay, maybe I'm being naive, but I thought the word from the Fermi bubble and from the wimpy jets you see in the X-rays, that it looks like the black hole should be spinning, and from the angular momentum profile of the galaxy, the black hole should be spinning in
I don't know. I don't want to. I haven't read papers claiming that. Maybe there are, but certainly the party line among the black hole astrophysics community is we don't know the spin or alignment of Sagittarius A star.
Okay.
So there's a hand, Bogdan, did you want to ask a question?
Yeah, I just wanted to ask because you talked a lot about how about the testing black hole physics, and then you said that the astrophysics had a problem. Is there any way for the HT to test any astrophysics, maybe?
Yeah, definitely. And in fact, one of the biggest impacts we had, I'm most proud of scientifically, honestly, is if you look at the M87 papers, they're all about how astrophysics doesn't matter, and that's wonderful because we can do gravity stuff. And I think that's wrong. And we've been going around saying you should do astrophysics. And the M87 papers said all the models fit. And so we can't learn anything. And then you go to Sag A star, and it's like the opposite. The papers say, none of our models fit. There's all this data teaching us about astrophysics. And so from this first measurement, especially of Sagittarius A star, it's very hard to do that because of the challenges involved with the source. But I think the mentality has shifted, and probably in 5 or 10 years, as there's more data and more people thinking about it, we really will start to see the data used to distinguish between astronomical models in an interesting way. I don't think it's there yet, but that would be super interesting. In fact, someone earlier asked about distinguishing spherical infall versus disk, and I said it would be hard. But then later somebody asked about redshift, and that was an excellent point. The fact that there's redshift kind of suggests the disk, I think. Okay, I'm talking out loud and rambling, but yes, I think they definitely can and will learn some astrophysics.
Okay, thank you.
I guess we're at the end of the questions, maybe. Everybody's exhausted. Not Sam. Still early. Okay, well, let's thank Sam again. I'm